going over this connection. So that gave them the idea, okay, well, if you can put multiple tones over here, we can actually transmit signals, multiple signals, or audio. So that's where the idea of his idea of being able to actually do the telephone came from. So this is interesting, and this actually goes, we'll get back into the bandwidth issue in a second when we get to some of the Maxwellians. But this was late 19th century, or mid to late 19th century when this was happening. And at the same time, we're all studying this idea of electromagnetic waves. And there was a huge controversy, not huge, but there was a controversy in the scientific community about what electromagnetic waves were. And so one of the reason why this ties in, Bell's work ties into this, is, and we've all experienced it, I'm sure I could generate it somehow here, but one of the things that had people thinking about the creation of electromagnetic waves and how we're actually going to be able to demonstrate them comes from this concept here. This is the telephone switchboard. So hopefully a lot of even the younger generation, myself included, has seen this, at least in videos or TV shows. Somebody actually plugging into a switchboard to connect a circuit between two endpoints. When you do that, it's the same thing as if your speaker is on or your microphone is on and you plug it into a jack. You get that awful noise, that loud, like, crinkly noise that comes up. This was termed extra currents. All right, so they heard it and they were dealing with it, and you try to suppress that, but this thing happened, this extra currents happens. So trying to figure out why this happened is kind of the part of the interesting story of the invention or the discovery of electromagnetic waves. Because what's happening, and this is what we're going to study first in our first GNU radio flow graph. So what's happening here is you're going from no signal to signal very quickly. So you have this not impulse, but impulse-like response to the system. So no signal to signal is a very sharp transition in time. So the first main lesson here, as far as from an educational perspective working with radio, is that short duration in time means long response in frequency. So we have these two properties that are instrumental in how we understand things. So, and by the way, all these flow graphs and examples and all this stuff are going to go onto my website, so people can download them and play with them. They're all fairly simple, but this is what the introduction is for. So we're going to start with this flow graph. This is what the term that we use in GNU Radio for basically a radio application. So we call it a flow graph because data flows, and so it's a graph, and data flows through it. It actually comes from the concept of process graphs, kind of an old CS theory. But so yeah, so every flow graph, and this is a thing called the GNU Radio Companion, and it's a graphical interface, development interface environment for working with GNU Radio. So you basically are able to graphically put down your blocks that make up your graph, your application, connect them together and run this. Now what this actually does is it builds a Python program, and that Python program is what's actually getting executed. And it actually executes C code. So there's like these three layers here. We have the graphical interface, the Python application itself, and then the underlying C++ library that is GNU Radio. So if I go to the canvas now, switch over to, we're on the wrong one. Okay. So what we do to create a flow graph is you pop open GNU Radio Companion, and you have this huge list of blocks over here, or list of categories. And so GNU Radio is full of these, a huge number of these blocks. And so each category will have, and so what we're going to want to do is like look at, it's probably, I was looking for our waveform generators, but that's far below. So let's look at modulators. You can open up, and so you can see in our modulation section, we have a bunch of different modulators, modulators and demodulators for FM and AM, well, FM for like analog stuff. We have a lot of digital modulation, demodulation, a lot of blocks in here. What's nice though is you can always just search. So, Control F pops up a search box, and we can say, I want a vector source, so you can kind of, almost, not really regex, but you can search for anything that has vector in it. All right. So we need to create a source. We need to somehow put data into our flow graph. And this is going to be in simulation. Actually, this isn't simulation because it has real hardware attached to it. But we have this source, so that's going to generate data into the flow graph, and we're going to process it somehow. to study this effect, all I've done is I've put an audio sync so we can hear it. Unfortunately, I don't like. We'll see how much we can hear it in this. Turn up my volume just in case. And then we're going to actually view it in time. And this is a really, I think, important thing for the study of signals and the study of radio is the ability to look at signals. So we drop down a time sync. So data starts over there and just flows down the flow graph until it goes into that sync. Now what's inside of this, if we just double click, I can never keep my mouse. We get to put in a bunch of different parameters. So we get to set the data type. So right now we're just going to work off of floating point numbers. Often you'll see complex numbers used in GNU Radio. We spend most of our time doing complex math work, and so complex numbers. Here we're simplifying it by just looking at a real number or floating point number. Now the trick here, no, there's also a repeat. So we're going to send out a vector. So we're going to generate a vector and pass it into the flow graph, but we're going to repeat that vector over and over again. So this thing is going to be constantly repeating itself. And what the value that's going to go into here is based on this con parameter. So it's a variable. And that's one of the things to note here. Everything that goes in here is actually Python code. So you can do a lot of programmatic stuff directly in the in this view here. So con is a variable that I'm going to set up and manipulate specifically for this purpose of studying this sharp rise time, the fact that we're going to go from nothing to connection. We're going to do that by having another GUI interactive tool called enable. Oh, sorry, this is actually unnecessary, so I'll disable that. That was for another study. Con is this variable here for a Qt GUI checkbox. So it's just, it's a GUI element, a checkbox. So we're going to check it to turn it on. So if it's checked, it's going to produce a value of 1, and if it's not checked, it'll produce a value of 0. And that's going to update that value in the vector source. So the vector source is now either going to be producing 0s or it's going to be producing 1s. Pretty simple conceptually, but I just wanted to make sure that we understood how we can kind of use variables in these parameters to go back and forth. So now I'm going to execute this flow graph. Now, you can't actually see it in this screen, but there's a bunch of toolbars up top, or you hit F6 and it executes the flow graph. So this is our time sync. So data is being generated. This is constantly updating the data generation and printing it to the time sync. So we're just seeing this. So along here is the time axis, and here's the amplitude axis. Oh no, this is on purpose. Yeah, it's scale offset on purpose. But then I'm going to, so it's just generating zeros, and as I hit the connection here, now I've actually captured that. So if I turn something off here, this is another thing that I wanted to point out here. There's a lot of interactive tools that we can use. So what I've set up here is a trigger to trigger like a O-scope trigger, a normal trigger. And so when the signal goes from 0 and rises, that triggers the scope to take a capture and hold that capture. But if I turn that off, if I just go to free run, now it's just constantly free running because there's no change in state. So it doesn't care. So we can turn it on, turn it off, back on again. And also when that's happening, listen to, if you can hear it, you just hear this little click, right? That's this kind of extra currents concept. So we can have this kind of interactive study to see it, to play with it. I'll turn the trigger back on here. Because again, what we're studying, there we go. What we're studying is this phenomenon that happens from going from 0 to a signal very, very fast. In this case, almost instantaneously fast. Now it's a sampled signal. So from one sample we're at 0, the next sample, so it's not infinitely small, but it's as small as we can get in time in this sampled signal. So what was causing this? That's kind of the question that people were asking. And how do we use this to our advantage? What kind of things can we learn from this? So I'll stop this for a second. Go back here. So as I said, Alexander Graham Bell kind of discovered the fact that we can transmit bandwidth over wires. So there was this idea that you could have multiple tones going at one time. How do we study this? Possibly it's one of the most important principles in electrical engineering today is the concept of the Fourier transform. This ability to convert a time signal into the frequency domain representation of it. So now he worked on a completely different field, actually, but it's been applied to electromagnetic waves pretty much ever since. So what we're doing is we're going to take this time signal, this very short duration time signal, this rise time, and we're going to try to study it from a frequency perspective. And that's something that they didn't quite understand in the late 19th century, was being able to use this property here. But we know how to use it. So let's make use of our tools here, because this is another, as I said, the ability to look at signals and look at them in multiple domains is a really important thing when studying signals and radio. So we'll drop back into our GNU radio system here, go into the next flow graph, which is just slightly more complicated, doing a little bit more processing, and added a different sync. So now instead of just looking at it in time, we're going to look at it in time and frequency, and that frequency sync is actually performing the Fourier transform. So we take that time signal and represent it in frequency. Really powerful from an analysis point of view. It's also pretty much the way that this Fourier transform is used in pretty much every cell phone being sold today. LTE is fundamentally based off of the Fourier transform. So like I said, massively incredible piece of mathematics that goes into this. The other thing that I'm doing, and this is kind of just to show one property of signal processing, is I've also dumped in a FIR filter, a finite impulse response filter. Filtering is, again, another incredibly important concept or tool in our signal processing capabilities. Not only is it a great tool, it's also a great way to study systems, because pretty much everything is a filter. You put a signal through something, that hardware, whatever it is going to filter it because it has a band pass response. It can't just pass every single frequency component from here to gamma rays. It's going to have some kind of a shape to it, possibly not even a flat, but sometimes an uneven shape to it. This is what audio people get really obsessed about with the response of the speaker system or the microphone, is getting the filter shape as smooth as possible. So we're going to throw in a filter here because we have to band limit the signal. We want the signal to be band limited. So now when I put that up there, and again, don't worry too much about the details of I'll show you some filter design tools at the end. But again, you can study how we do this. But this is just going to be a low pass filter. So now we're going to look at this signal, the same concept I'm triggering off of this rise time connection here. And now when I do make the connection, first off, notice that instead of being instantaneous in rise, the filter gives us a little bit of a delayed response and a shape to that. So this is, again, if you've ever looked at signals on an oscilloscope, you've probably seen that phenomenon, quite popular or famous, well known. But also at the same time, not only are we looking at this in time, but we're also now able to look at this in frequency. So this is the frequency domain representation of that signal. And what is that signal? Well, there's the transition period itself, so it's not just a 1, but there's a lot of 1s. It's just a signal that's just on. Has no frequency component in that always on state. It's a DC term, right? It's 5 volts or 1 volt or whatever we want to call it. So that's why we have this really large spike at the DC term of the frequency domain. And again, unfortunately, the screen is weird here. All of these plots are going to show you positive and negative frequency. So this is minus negative frequency over here. Right in the center here is the DC term. So this is 0 hertz. So huge DC term because we just turned on a DC signal. So that's what we see here. But again, the important concept here is short amount of time, long frequency response. So what this signal has also, or this GUI has also done, is captured the max hold. So I can turn on the max hold and see, because it's a very little amount of energy happening very quick over a period of time. So a lot of energy, very little power, because it's happening over a short period of time. So this curve here is kind of the Fourier transform over a certain number of points that we can see the effect of a very short period of time. So this long response in frequency. And remember, I filtered it. So that filter kind of shows up here at the edges. So it's a very loose filter, but it's kind of, it's rolling off there at the edges. So this is the idea that these guys had when they were trying to study electromagnetic waves. Okay, if we know these extra currents are producing this long response in frequency, what if we could capture part of that frequency response? So we know how to generate tones that are very high in frequency because these impulses are very, very broad bands. But how do we capture it? So going back to our slides here, that's where we come to another famous mathematician of the 19th century, James Clerk Maxwell, and the famous Maxwell's equations. This is where the interesting things come into play here. A lot of the people at the time, the scientists at the time, again, didn't understand this time bandwidth, the Fourier transform relationship that we were able to just look at. So he comes up with his theory in mathematics behind the theory of Faraday's induction. So the idea of inducing a current in a system, so the change in bandwidth over, change in the magnetic field over time in this equation is related to the generation of the electric field out of it. So it's not that you just put a magnet in front of something and you get a current. It's the change in the magnet that induces a current somewhere. So this concept of time, change in time, is of course directly related to frequency. So the Maxwellians, the people who believed Maxwell's equations, who understood the math, understood this concept that this high rise in short time period rise time based on the equations is going to produce a high frequency response. You know, they had this, they already had this understood. Their question was, how do we actually study this? Now, for the sake of time, I love this this experiment, but for the sake of time, I'm going to try to shorten my my discussion of it. This is a Leyden jar. Now, a Leyden jar, it's a specific design, but what we would know it today as is a capacitor. So I'm able to charge this capacitor up with a static electric charge, and then so I can build up, you know, thousands and thousands of volts on this thing and discharge it. And so it's a spark, it's a static shock. It's just a large static shock depending on how much you charge this up. And when you're playing with this, it starts to hurt after a while. So you come up with other ways of doing it. But this is an old 19th century tool that the scientists used to study electromagnetic fields and electricity in general, static electricity in general. So I bought, this was a present last year, and so I played with that, and I wanted to see, okay, what does this impulse look like? You know, I talk about this, I know this impulse and this math and all this stuff, but what if I actually was able to capture this and see what the signal looked like? So I charged this up, and then I used this thing. This is a B210. This is a USRP, one of the hardware systems from Edis Research that we use. In fact, I've got a B200 sitting right here that we use in GNU Radio to do signals. So we can receive with it, we can transmit with it. So in this case, I'm using this 19th century tool to generate a tone and a 21st century tool to receive and capture that tone. So that was really fun. Now, what I'll just point out here is, without going into the details of why, this is perfect. I mean, this was so amazingly perfect that I was surprised that it looked as good as it did when I captured. This is a real live capture, and that is a filtered impulse response. I mean, it's actually like, when you, I did a lot of time studying ultra widebands back in grad school, so this is mathematically very significant to me. But this is the thing that they were able to do back in the day, is generate these very sharp impulses. And again, knowing Maxwell's equations, we understand that they have this long bandwidth response time. So this is actually only captured at 2 megahertz, only because I didn't feel like filling up my entire disk with like a 32 megasample, 32 megahertz at a time, which would have given me a really an even sharper pulse. So I wanted to, so this is kind of an inspiration for studying the kind of the follow-on effects. And Oliver Lodge, who is one of the highest or most well-known of the Maxwellians, I love this quote of his, that, and this is really important, I think, again, back to the ability to use our tools to visualize signals. So it's ridiculously easy, right? Remember I said you just plug something in, and that's generating high frequency. So they knew that it was ridiculously easy to generate it, but he had absolutely no idea how to receive it, how to prove that it was being generated. But so that's where we're going to try to head to in a second. Now remember I said everything is band limited. Everything is a filter, like almost like in, without too many things that I can think of off the top of my head. Everything in the world is basically a filter. So we're going to use this. We're going to play with this filtering concept. And this generation here, this flow graph, called impulse generator is, okay, let's take this Leyden jar experiment and try to recreate it. Let's simulate this, this experiment. So again, fairly easy to be able to generate an impulse because it's just a series of zeros and then a a 1. So again, discrete time sampling here. So we just generate a 1 and then a bunch of zeros. We just kind of, we'll repeat that so we can see this phenomenon over and over again. So we're going to generate that by using this form of for the vector source. So 511 zeros followed by a 1 followed by 512 zeros. So a 1024 point vector that's just going to get repeated over and over again. And again, just remember, like, that's Python. That's a Python expression basically to concatenate a list. But our receiver, our systems all have noise. So I wanted to simulate the noise. So I'm using this, this fast noise generator. And I just kind of approximated the amplitude to get it to look pretty similar. And it's Gaussian, so it's a Gaussian noise source, a random generation of Gaussian variables. So that's where we come up with the term additive white Gaussian noise. So we're going to take Gaussian noise that's pretty much white over the frequency, our bandwidth, and just add it to the signal. So come in with a bunch of ones and zeros, and we just add some noise to it. Now here, this is a detail here called the throttle. I didn't have it in the last flow graphs because I had an audio sync hooked up. That audio sync has a sample rate. And we have to understand sample rates if we're going to do anything with digital signal processing. So the sample rate of the audio card was, I think it was like 32 kilohertz or something like that is how I programmed it. So that was actually clocking the system, because that audio system can only push data out at such a rate based on its 32 kilohertz clock. So GNU Radio is going to push data to it until its buffer gets filled up, and then GNU Radio is going to hold back. And then as soon as that buffer clears up, we can push more data into it. Here, this is pure simulation. I'm just generating samples as fast as my computer can generate them, and I'm just going to display them in time and frequency. I've got nothing gating me. So if I just launch this without something that's kind of holding the system back, it's going to go really, really fast. And if you have too much in your flow graph, if you're trying to do too much, it will eat as many resources and CPU cycles as it can get from your computer. So the throttle is an arbitrary way to hold this back, to kind of smooth out and slow things down. It's a very bad throttle. I mean, it's a very bad gating system. It just uses the system clock, which is not accurate to more than like milliseconds, if that. So it's I'm sitting here at 2 mega samples per second, plus or minus the reality of the actual clock. But again, we're just using this for simulation. As soon as you put hardware in the loop, as soon as we add the audio system there or a radio, get rid of the throttle, because now the throttle is acting as a competing clock. And so you have this thing called the 2 clock problem that comes up, with 2 guys are trying to independently sample your system, and because that's a bad one, it's going to perturb your ability to actually receive or transmit properly. So this is pure simulation here. I start this. Oh, and the filter, instead of doing a low pass filter, I've actually I'm using here a Gaussian shaped filter. The reason why I did this is because I wanted to narrow the signal a little bit so that we can study our receiver in a second. But also, as I said, I studied a lot of ultra-wideband, pulse-generated ultra-wideband, where we were doing 4 gigahertz wide pulses. But it was generated by a Gaussian monocycle. So Gaussian monocycle in time, take the integral of that, the Fourier transform, it's a Gaussian in frequency as well. And hopefully that's the most math I'll get into today. So I just wanted a Gaussian filter because it just looked nice and it's going to fit it fits the story. But here we have the impulse going up there. Like I said, every 500 or every 1024 samples, we have this one, and then it's getting distorted by some noise, and then filtered by this Gaussian filter response. So this is my way of playing with this idea of impulse generation. Let's see. Is there anything else? I'll point this out again. I'll go over an easy way to look at filter generation in a few minutes, but we're using a tool here to just generate a Gaussian filter. I think that's pretty much all we want to learn from this flow graph. Okay. So in this case, I'm experimenting like it's a 200 megahertz signal spectrum signal, filtering with that Gaussian filter. And now the trick is to be able to sample this. How do we actually get this, this signal back? And that's where this guy comes in. And he was really the motivation for this talk, is to study how did Hertz do his work? What was the original experiments that Hertz did, and how can we use them to study software radio? And then in researching this, reading a lot of books, this is the quote of Hertz that I just love the most. Somebody, after his first lecture at Karlsruhe, Karlsruhe University at the time, he demonstrates that he's able to do these electromagnetic fields, and somebody says, "That's amazing! You've proven Maxwell right. Everything works as predicted. What good is this?" And his response was, "Well, nothing, I guess." So maybe one of the most fundamental or important, commercially for sure, discoveries in history. I mean, you think of the billion-dollar cell phone industry, kind of goes back to this thing which was just a lark, just for fun. So, what did he do? What did he do that Lodge didn't understand? Because Lodge, as he said, didn't have any clue as how to actually capture that signal being generated. And that's what this apparatus does. So it's a spark gap transmitter. So you got this transformer here generating a high voltage, and then there's a spark gap that gets generated at approximately 100 million times per second. So roughly sitting at a carrier frequency of 100 megahertz, you generate this spark around there. And so 100 million times a second, you get this very broadband signal being generated. That signal is then transmitted over this dipole-like antenna structure. It was just two kind of loads that he had that kind of approximated an antenna. It's kind of like an early form of an antenna. But that's why I wanted to filter the signal, because this is a filter, right? I mean, even though this is generating a broadband signal, the response, the electromagnetic properties of this load system here, this antenna, is going to have a filtered response. So in a way, when you're studying antennas, you can study them in terms of filters and how they behave in frequency, what kind of shape they're going to perform in frequency. And so it's very difficult to make broadband antennas because they all have a shape to them. We figured out how to do it now pretty well, but it's still not easy. A dipole tends to be very, very structured around a certain wavelength of the signal. So we're generating this filtered signal, and all his receiver was doing is just this large loop here. And you could, when he matched these, basically he's doing matching of filters. So in another word, he's doing impedance matching. So once he could figure out what the impedance matching was, generates a signal here, you get a spark between those two balls at the end of the antenna. So for all of this work of trying to receive signals, how do we look at signals, how do we know that we're doing it, the entire receiver is fairly trivial. Except that he had to do it the right way. So here we're going to get into a little bit more interesting GNU radio flow graph, where we're going to try to not only generate that impulse, but what do we do to receive it? And we're going to receive it by approximating this antenna as a filter in our flow graph. So also one thing to point out, instead of having all these orange ports here, so these are the ports that we connect, I've now switched them, and so just so you know, to connect up blocks, you just kind of hit one port, connect to the other port, and it creates this connection. The blue now, we're now dealing in complex numbers, because I wanted to do a complex bandpass filter. Don't worry too much about that if you don't want to go into to complex numbers. I just wanted to point out why the change from the color. So visually, you'll see what's happening without having to really understand why. I can certainly answer the question if anybody wants, but we'll just go from here. So that top section there is very similar to what we had in the previous example, except now it's complex. So I'm generating complex, an impulse, adding some noise to it, putting that Gaussian filter on it. So that's our transmitted signal. This filter is our receiver. And so I'm generating these receive taps. So notice here I just put in this variable, Rx taps, which I'm defining up here. And if I can expand this, we can see a little bit about what's going on here. There we go. So I'm using, again, our filter design capabilities in GNU Radio. We're using this API call into the library, and I'm passing in a bunch of parameters. So I'm gonna create this receiver. So I'm gonna have this filter, this bandpass filter with these different parameters being set. Now the bandwidth and the transition bands that I've got set here are variables that I've defined elsewhere. And apparently not, oh, came up over here. So I define these as static values. So I've got a bandwidth, so the antenna itself is gonna have this certain bandwidth based on this number here. Transition band, again, if you're not familiar with filter terminology, it's just how the shape and just how the roll-off of the filter looks. But the important useful tool is this range block. So again, remember we had that connection, the checkbox to turn something on and off. This is now a slider. So we can put down a slider onto our application, and don't worry too much about trying to parse what that is. I'm just giving it a range, just so we can just slide this range around our frequency domain. And that's gonna update the filter as the system is running, so that we're gonna basically be tuning our antenna, like a live tuning of the antenna, to be able to see the signal. So when I run this, let's see, I'm gonna turn off the imaginary parts. So we're just gonna be able to look at a real signal here. So that blue signal on the top there is the transmitted signal. That's what we're trying to capture, but we're just gonna look at it so we can see what we're trying to capture. The green is our receiver. So this was the difficulty was, I mistuned. My antenna is not tuned to the right frequency response, so I'm getting very little signal coming through here. And we can see this in the frequency domain. This blue signal is the transmitted signal, and the red is after going through our receiver filter, our mistuned receiver filter. So first of all, notice, yes, we're seeing signal here because no filter is perfect. There's always energy leaking through our filters, but this is in decibels, like decibels relative to a 1 floating point number. So think of it as a dBm if you're into like amateur radio guys here will easily understand dBm, but it's a log scale. So we're going from minus like 45 down to minus like 120. In log scale, that's a huge decrease in power. So we can see the power from the transmitter up in the blue, and even though there is power coming through here, it's not really showing up in the time because it really is suppressed so much in power. But there's this little guy sitting over here, and that's my filter. That's my bandpass filter that I've created, but I've started it detuned down here. But yeah, so I've got this center frequency slider here, and I'll just use the buttons here so I can move the center frequency of that filter. So I'm recreating the filter taps to generate a new filter response. Go there. So come on, trackpad. So as I change it, as I increase the filter center frequency, you can see how the can I keep this? There we go. You can see how the response of the incoming signal is now changing. So now more energy is coming into our receiver, and notice the green there is starting to come back up as we're getting more and more of the energy. So if I can perfectly tune. Close to it, yeah, close enough. If I can perfectly tune my receiver antenna, if I can create the loop, essentially the diameter of that antenna is going to be its frequency response. I can place my receiver in the center of the transmitted signal and capture as much energy as I possibly can. So notice how the receiver has a smaller bandwidth than the transmitter. So I'm just trying to center it so that I get as much of that energy as possible. And so notice two things. The green line is slightly smaller than the blue line. We have some loss, energy loss, and it's also delayed in time. That's because it's a filter. There's a time delay, there's a group delay that a filter has. It takes a little bit of time for the signal to pass through that filter, which is again actually the same as an antenna. So here we have the ability to tune our system while it's running and play with this idea to see how we can capture this impulse response. Okay, and I think that's the last that we need to learn from that. yeah, this just goes over basically what I said about tuning and mistuning our signal. All right, this is just for us later. So, just got about 5 minutes. So I just want to pop this up really fast then. Again, we did a lot of work here. I showed you a lot of things that had filters being generated. So, and again, filters are hugely important when you're trying to do any kind of signal processing. And there's a few kind of gotchas that we need to be able to play with. I can't do that. Let's see. So if we were able to see the toolbar, again, I don't know why the resolution is doing this, but there's a tools menu bar, and there's a filter design tool that GNU Radio has. But I'm just going to launch it from my desktop here. So we would. There we go. So what we can do here is play with and design our filters, and we can study the filters in different ways with this tool, so that we understand kind of what the consequences of our filters are. So not going into the details for a filter, Hamming window versus Blackman window, things like that. Let's just look at it from a low pass filter perspective. So we're going to low pass. So the pass band of this filter, we're going to pass all frequencies up to 50,000 kilohertz. And then we're going to attenuate that signal afterwards. But we're going to tell the filter that you have 10 kilohertz to stop the pass band and then slowly degrade into the noise floor. Go down here and hit the design, and there's our filter. So that's what that filter looks like. Passes everything. This is a frequency response. So think of it as multiplying your frequencies together. So anything being multiplied in the pass band is being multiplied by a 1. And then as we go into the transition band down to the stop band, we're multiplying by a very low number in decibels. So we're suppressing this signal dramatically. Something to keep in mind here when you're playing with these filters, and again, it's a very common misunderstanding from people just getting into signal processing or just getting into radios, is the consequence of your filter. So in this case, the consequence of the filter is that I have to, that the number of taps of this filter is 59. So I have to do 59 multiplies and adds to compute the filter. So the longer your filter, the heavier its compute power is going to be. And we want to minimize that. So how do we minimize the number of taps? Well, there's two things. We have kind of 2 degrees of freedom here, and I'll only play with one for today. But if I go from 60K, so I gave myself 10K to go from a 1 to 0. So now if I do 70, so I have 20K, I've now relaxed my filter from a signal processing perspective. But now if I design this one, I went from 59 taps down to 29 taps. So now I have to do 30 fewer multiply and add computations to run this filter. But notice that it takes a longer bit of time. So it's a sloppier filter, which can be okay, right? That's the thing that a lot of people that come to us with problems. Why doesn't my flow graph work? It's taking it's taking too many computations. And it's because a lot of people have done something like this. I'll do 51. 581 taps. But that's a really nice filter, isn't it? Right? I'm not getting any other signal in. But people don't, you have to study, you have to understand the response of the entire signal in the system that you're working with, because it can be okay to have a long transition band. What that's going to do is it's going to pull in extra energy, maybe a little bit of extra noise, and maybe a little bit of interference. But you have to be able to balance these ideas of the cost of the computation versus the cost from a signal processing perspective. And this is and so I point out this tool because I want to make sure that, knowing that it exists, you can use it to study your filters. Let's go back to a cheaper filter and notice that we can go over here, we can actually see the taps. So we look at it from the frequency domain, and now we're moving into the time domain here. You can look at the phase response and the group delay, which is, let's look at the phase response here. The delay of the filter, 29 tap filter, 27 tap filter, is going to have a delay based on the number of taps because you're kind of moving through these taps one at a time. So it's going to delay that signal out. So 27 taps, obviously, a much shorter delay than 581 taps. So again, that's another trade-off that we need to be aware of, is the delay that's going to be produced in our system. And so there's plenty of other things to play around with. If this were a filter lecture, to spend a lot more time in there. But I think this is a really useful tool to play with, to learn about filters. But also when you're actually designing a system and you actually want to design your filter, I go to this all the time. And there is actually a way to save this filter. I just you just go up to File, Save, and it exports it as a CSV file. It could be more clever, but everything reads CSV. There's not that much data to capture here. But so you can save it, your favorite filter that you've designed here, and pull it up later. All of the design methods that are being used in this tool are also programmatically available in GNU Radio itself. So I pulled that up and I showed you FOSDEM.Gaussian. So that's basically if I change this, where's my mouse? There it is, somewhere up there. So I could actually create that Gaussian filter here and look at the magnitude response. So there's a Gaussian filter. So this is just a graphical interface on top of our calls, our function calls within GNU Radio. So yeah, you can do a lot of playing around from that perspective. Okay. So there's just a little bit of that. Okay. All right, I'm running right up against time here. So I'm just gonna, there's some slides at the back here, just to point them out. Kind of talking more about the project itself, that there's this community and this a whole bunch of these out-of-tree projects, so people building projects against GNU Radio, trying to show you the list of possible block categories that we have available. So it's a massive list of available algorithms in GNU Radio already, plus this entire ecosystem, this entire community of developers who are building their own sets of tools and blocks and algorithms. We tend to be generic, try to be generic inside GNU Radio, so very general stuff, filters, adders, multipliers, things that can be used against many, many signals. The out-of-tree projects tend to be focused on particular signals, LTE, Bluetooth, ADSB, AIS, those types of signals. So we try not to get very particular inside of GNU Radio. But I just wanted to point that out before going back to the final demo part, because I wanted to make sure that we understood everything I was doing up here was in simulation. Well, there was the audio portion of it. But as I said, we also have this ability to connect to hardware. So we have these hardware tools like the USERPs and other devices, the HackRF, the RTL SDR dongles, that we can connect into it. So we can go from our generation of signals here, and here I'm generating two signals at different frequencies. And I just wanted to do sine waves because, well, we were, this talk was inspired by Hertz, and that's the unit that we use to measure sine waves and frequency is the Hertz. So multiplying two signals together, just going to create a weird signal that I'm going to transmit over the air. So I'm going to, I've put down this block here, this USERP sync, to be able to transmit it over the air. So as I run this, it's going to take a little bit of time to load. And so this guy is now transmitting at 428 megahertz, a fairly small amount of energy. I'm going to increase it just enough. So I'm just generating a little bit of a sine wave here. Oh yeah, the B200, actually, you need to kind of give it a lot of gain. There we go. So I'm generating the signal here, and I have GNU Radio now running on Android, where I'm pulling the signal in through, so I just have the RTL SDR dongle connected through to GNU Radio, and this is actually filtering the signal. I'm just using a filter because I want to do something more than just, receiving and displaying. But yeah, so that's that signal being transmitted from there. So this is our new project right now, is to get this a little bit more stable and ready to ship out the door. So we'll be seeing a lot more of these tools soon. Okay, do we have time for questions? I'm like a couple minutes over, so. Oh really? I thought I was done at 10. Okay, so. Well, I'm done at 10:15, but let's make time for a transition. So let me turn this off. And let me just pop up, let's see. Yeah, let me just pop that up. And so I guess, yeah, are there any questions? Well, the bandwidth of the signal. So the spark gap. Are you talking about the Hertz experiment itself? I actually don't know. I don't know if we know what the bandwidth of it is. Like I said, he was generating the spark at 100 million times per second, and because it's a spark, because it's this instantaneous spark, as my Leyden jar experiment showed, it does have a very broad frequency response. But then it's being passed through this antenna structure, these loads that he had. So I think the bandwidth is going to depend mostly on the load of that structure. So we'd have to study what the material was, the size of those loads, all that. I'm sure we could kind of roughly calculate it if we went back and saw his original experimenters.
It's a few gigahertz.
Even Hertz's experiment was a few gigahertz?
It's going up to some gigahertz.
Okay. So yeah, broad bands. Precisely, yeah. So
It's your filter.
yeah, exactly. Precisely, yeah. So yes.
That is illegal to experiment with spark.
I don't know. So the thing is, so one of the interesting points was I showed in time what that looked like. I can't show you the frequency response. The power, because it's so quick in time, the amount of power being generated is so small. There may be a lot of energy, but it's energy, well, no, there's actually very little energy as well. Energy over time being power. So very, very little power being generated. So probably because most regulators only care if you rise above. If I was generating this continuously, that's a problem. But just once every few minutes, nobody's going to see it. That's right. So the problem with the generation of wideband signals in software radio is still you still have to have specialized equipment, high-speed FPGAs. Doing things over USB, you're not going to get that kind of bandwidth. So you can experiment with OFDM, you can experiment with CDMA, which was a competing standard. The pulse generation for real true ultra-wideband, that's not happening in these types of systems. They're just not designed for it. The hardware for a pulse-generated ultra-wideband is very, very specific and kind of highly tuned. So. Ultra-wideband was huge about 10 years ago, and we never really figured out the right application and not only being able to do it, but also being able to do it in a commercially viable way where receivers and transmitters, nobody really got there or needed it until, so maybe in 10 years it'll come back in fashion.
All right, if you're going out,